Good afternoon. Welcome again for the 1 week special online course on this advances in Earth observation data for hydrometeorological hazard assessment and process based models. So, the first lecture today, I'll be discussing with you about the recent advances in the Earth observation data as well as the various techniques which are used for the hydrometeorological hazard assessment. I will cover the major satellites, the geospatial data, as well as the few case studies which will be elaborated in detail in coming days by the faculty of WRD. So this is the overall outline of the this presentation today. So first, just a brief overview about the hydrometeorological hazards, and then what are the various Earth observation data from Indian Space Research Organization, as well as we will see there are other new space players which are providing the almost near real time data for monitoring such hazards. And then starting with the river basin, as discussed in the previous introductory session, starting from the where the river starts, that is from the mountains where we have this cryosphere, and what are the hazards associated with the cryosphere, and then coming downstream where our hydrological modeling of these extreme events is very input. And then as you comes into the flood plain, the flood is the major issue where the integrated flood early warning system has to be done. And then some extreme events modeling, I will show the study and how those inputs has been integrated into these modeling framework. And finally the concluding remarks. So if we see the hydrometeorological hazards, so in this and these hazards constitutes about 60% or sometimes even higher percentage also of global hazards that are known to reoccur, and they are the most recurrent hazards. And floods is the major one, where you have the flash floods due to the very high precipitation in a particular area, or then you have the glacier lake outburst flood or the landslide lake outburst flood. During the cyclone, you have the storm surges. Then you have the cyclone will cause the high wind as well as high precipitation, which will cause extensive damage throughout the world, including tornadoes. And then if you have the untimely hailstorm, it can cause the damage to the crops and sometimes to the property as well. And in the mountainous region, we have this heavy snowfall will result in a avalanche. And if you have the very sustained snowfall with the high winds, you can also have the blizzard, which will cause disruption of the normal human life, including disruption in the traffic. Then you have the severe thunderstorms, and if you have the scarcity of the water for longer duration. For example, if you see the example of Ethiopia or the some regions in US and Europe this year, we have seen significant high heat waves, plus you have the drought, which results into the scarcity of the water. And what are the techniques using remote sensing and modeling techniques which help us to monitor such extreme events, either access or the scarcity of these water sources. So what we just for an example, I have chosen here the flooding example. So this there is a science of the flood model, and which give us an idea how we can create the flood model. So the most of these hydrometeorological hazards, heavy precipitation is the main input, which now it can be monitored using remote sensing. And this consequence of this one will be the flood, inundation, damage to property, humans, animal life, and damage to the crops. So starting from the how much is the extreme precipitation at the source or in a given catchment area, the consequence of this will also be can also be monitored using remote sensing. And if we combine various thematic layers like the digital elevation model, land use, land cover, and the soil properties, we can also estimate what are the areas and how the excess runoff is going to be generated, and how much water is generated in the river system, which can cause the flooding in this particular area. And also the post floods, what are the inundation area, how much property is damaged, so that can also be seen from the directly from the satellite data. And this I will come back to this particular point, how we create the flood model, especially which is being used for the flood forecasting systems which are running at global, regional, and local scales. Now, if we see the progress, I will start with the cyclones, because this particular hydrometeorological hazard, which is known to reoccur in a given particular window. For example, October, November, in the east coast of India, we will have the regular occurrence of these cyclones. So there was a 99 super cyclone which was there, and it caused a huge amount of and this hazard turned into a major disaster, because the at that time the early warning and the disaster response was not there. So if you see this particular two animations, so one is for 99 and one is, I think, for the Phylin super cyclone in 2013, 14 years after this. So satellite data at that time also, it is providing the cloud cover, cloud top temperature, and they are the geostationary platforms. So every 15 to 30 minutes you get this information, and these are some of the other layers like the outgoing long wave radiation, precipitation. And then this information, if it is integrated with the disaster response team or this evacuation, that is the ideal situation. But that was not present in 99, and more than 10,000 people died due to the high winds, the inundation, and the damage associated with the destruction of the houses during this particular cyclone. And 14 years after the super cyclone, this Phylin also, so although there was some structural damages, but the human loss was minimum, because as you can see, this center of the cyclone, we call the eye of the cyclone, the prediction capability, where the satellite data is ingested, ground observation data is ingested in close collaboration with ISRO and IMD. So we can predict within few kilometers that the landfall of this cyclone is going to take place in this particular area. So once we know the landfall of the cyclone, and also we know at what time it is going to occur, and now it is almost 3 to 4 days, and sometimes if you start from the genesis, it can start early also. So we can predict this very accurately, and then the all the government and the other NGOs based disaster response, like the evacuation of the areas from the maximum where the cyclone will hit, the events will be higher, so the people are evacuated from those places, and now we have the cyclone shelters which are there, so it will minimize the loss of human life. So this is the major contribution of the satellite and the modeling technology, which results into saving of human lives. Now, if you see the Indian Earth observation mission, so depending upon the what kind of hazard we have, for example, for the meteorology and for the precipitation and for the cloud movements, it is always the geostationary platform which will be used. Apart from the geostationary platform, because we need to see through the clouds, and we want to see their various properties like the humidity, air temperature, pressure, all those things. So in those cases, we also use the microwave sensors. For example, this Megatropics Madras sensor is there. There are sounders available with these satellites. And then for the ocean and this one, we have Saral Altica and Oceansat 2, which will give us the water level in ocean and rivers. Then for the damage assessment, we need to know what are the areas which is going to be damaged at high resolution. So this cartosat series will give, and most of these meteorological, hydrometeorological disasters, they have very strong dependence on the topography, whether it is the flood or whether it is avalanche or the tsunami. You need to have very good quality topographical data, so no, you can exactly know if water level by rising by few centimeters to few meters, how much area is going to be inundated. So one is the element at risk, second is the topography from the cartosat series, and then you have this resource set series, which will give you the wide area coverage and also high resolution data in the list 3. And during the floods, as we will see, some of you might be knowing this, during the cloudy condition we need to see through the clouds. So that time period, we use the radar imaging satellites. So in this example, dsat 1 is there, and 1A, 1B, and the 2 series, which is going to come in future. So to summarize, this is the Earth observation sensors which are presently are being used, and also a lot of research has gone into this to improve their spatial and temporal resolution, plus the accuracy of these models. So if you want to estimate the precipitation from the space, you have to make use of the both optical IR passive radiometers and active radars. And this global precipitation mission, for example, this is the best example, where now before that we have this tropical rainfall measuring mission. From 99 to till date, this algorithm has been improved upon, and it has combination of precipitation radar, which will see through the clouds and will give you the vertical structure of the clouds. And then you have the this GPM microwave imager working in 13 channels. So higher channels are sensitive to the snow, and the lower channels sensitive to the rainfall. So this will give you at 0.1 degree, which is approximately 10 kilometer, and every half an hour. So this time series, the TRMM data has been reprocessed, and you get this time series from 99 to till date satellite based precipitation. Although there are certain accuracies, especially in the very steep mountains and in a highly vegetated area, but overall its accuracy is fairly good as compared to the previous precipitation products from the space. Now this we will discuss water bodies mapping during the flooding condition, and how we monitor the snow cover area, the water level, especially during the normal season and during the flood season. So this soil moisture, one is the agricultural application, the second application, because the earth before the flood, it can also act as a storage in the topsoil as well as in the groundwater. So the absence or presence of soil moisture can play a major role in the flood forecasting. Similarly, as I told earlier, topography is very important. From earlier Survey of India topo sheets to the current state of technology like UAV based topography or airborne lidars. Then we have the global missions, which gives us the global digital elevation models and the DTMs, which can help us to monitor and model the floods, the avalanche, and other disasters. The last one is related to the other water management, like the crop area management and crop water requirements. So at present, when we are talking about hydrometeorological this one, so these variables like the rate of change in moisture, the surface water, the storage, so this precipitation, evaporation, discharge, so they are all linked with certain kind of satellite data. So these satellite data, they are progressively increasing their spatial and temporal resolution. I gave the example of latest GPM data, and then when we run these models in a data assimilation mode, our accuracies will significantly increase in the estimation of these variables, so that we have a better control over the water which is available in a particular city level, or during the extreme events in a given watershed. So this is just an example of the precipitation which I have discussed earlier, and this all data, it is freely available. So there are three runs: early, late, and the final. Early you will get within few hours, late you will get in 24 hours, and the final you will get after few months. So you can process this data as per your need. Then starting from the headwater reaches of Himalaya, like your Indus, Brahmaputra and Ganges river, where they are originating, we have this satellite derived snow cover for the last 20 years. And the area where we have lot of glacier, for example Chenab basin, their relative contribution to the minimum and maximum snow cover area is higher, as well as their melt runoff contribution to the main river is higher. And these area you will have more incidences of avalanches, snow avalanches, glacial lake outburst floods, and also the flash floods, where you can have combination of snow melt, rainfall runoff and other hydrometeorological hazards. And these areas are also areas where we have this dams, especially for the hydropower and the water storage. So the safety of these hydraulic structure is also dependent upon these normal snow melt for the water management, and the extreme events for their design discharge capacity, especially for the extreme events. So just this year in March and April, we had this significant temperature rise of almost 4 degree in March and April. So although snowfall up to February it was normal, but if you see the 2021 image of the satellite here, in this case Sentinel-2, and if you see the same image of that particular week or day, 2022, you can see significant reduction in the snow cover. So although snowfall was same, but 1 year ago the snow melt has significantly increased in 2022 due to that sudden increase in the air temperature during the spring of 2022. So such kind of phenomena can be easily monitored with the help of the satellite data. Now the second one is the glacial hazards. So glaciers, this is an example of Gangotri glacier. So as we know, glaciers are the moving rivers of ice, and due to the climate change and other activities, this snout, what you can see here, I will show at the end of slide. This undergoes a various geomorphological changes. So if these lakes are forming continuously, if there is a blockage of water due to landslide or due to the proglacial lake, it may cause disaster in the future. And because in the border areas our troops are also there, so all the winter time they have to be there. So crevice is also one of the hazards which are always persistent in these high mountainous region. So just to give an example of all weather capability of the earth observation data these days, this is a image of the peak winter 18th February 2014 Landsat data for the Gangotri, and this is the 18th February 2014 EOS 4 data, not the EOS 4 but the reset one. Now it is 1A renamed as EOS 4. So you can see in the peak of winter also, because this is active microwave, the wavelength is 5.4 centimeters approximately. So it is able to see through the dry snowpack, and I can easily see the debris and the moraines and the clean ice which is below this sorry below this dry snow. So the all weather capability, you can visualize this, what are the current scenario, the surface scenario in a glaciated terrain in all the weathers. Then these are the crevices, just an example I have given the Cartosat 2 data as well, this plus the reset 1 data for the Antarctica. So Antarctica also we have our two Earth science stations, Maitri and Bharti, and we do go for the expedition in these areas. So this location of crevices is very important. So this radar data, due to penetration capability in the dry snow, they are very effective in monitoring of such crevices. Now recently in the first week of October and last week of September this year, we had excess amount of precipitation, and in the Uttarakhand region we had lot of snowfall, unusually high snowfall in the higher reaches. So we have ordered this data, and for those who work with the Indian observation data, they must visit this Bhunidhi website, which is the new web portal of our NRSC ISRO at Hyderabad. So there is a one more Bhunidhi is the traditional one for data ordering. This is Bhunidhi Vista. So you can visualize all the data. This is from the EOS 4 data for the 9th October for this Dokrani glacier area. So this is the background image, plus in the radar data also you can very clearly see, because during the snowfall event this is the snow free base data, but during the actual event and post event you won't be able to see this kind of images. So this EOS 4 data you can clearly see the crevasses, and this is the particular area where we had this avalanche where 20 mountaineers unfortunately lost their life. So such kind of all weather capability can help us to mark the danger zones, and then to ingest this data in the real time information to the mountaineers, tourists, or the troops, so that they can plan their activities in a better manner. So and this is about the glacier. Then in the excess of the snow will cause the avalanche. So some of you might have already visited the Atal tunnel, and some of you might have planned to see the Atal tunnel in Manali Rohtang area. So when you go from Solang Valley, and then somewhere here you have this Atal tunnel. So along the way you actually cross through the almost 10 snow avalanche sites. So these 10 avalanche sites have a source area where in the each winter you will have the accumulation of the snow. This is the typical example, the accumulation the snow where the formation will be there in the middle zone where it will go, and lastly where it will be going downstream and meeting the bottommost channel or the river. So where we have the road crossing. So for modeling of these avalanches, what we need the digital elevation model. Again, it comes from the either from the Survey of India or from the drone or from the satellite based data. And then you need the snow depth, you can get from the ground, or you can take it from the satellite observation. Then you have this ortho rectified image, high resolution latest one, which will give the friction parameters, for example the forest map. So this is one example using one of the popular models, rapid mass movements model, which has the compatibility with the GIS. So you run this model, and basically it solves the Salm-Olmy equation, and one of the lectures will cover in detail. So solving for basic mass and momentum equations, you will get how much velocity, how much momentum is generated once you release this avalanche, and you can very nicely visualize this data in the GIS. So this is just an example of using the traditional SRTM or the 30-meter DEM, and then using the high resolution topo DEM for this area. So once you know the exact pressure and the velocity in this particular area where your vehicle will pass, and if you go there, there will be a snow gallery. So inadvertently you may not realize that this is a big snow avalanche sites, because you are going through the snow gallery. From the top avalanche will grow, from the bottom excess flood water will go. So such kind of geospatial data help us to better model these such extreme events in these mountainous regions. Now in continuation of that, now we have a lot of big data and open source GIS like the quantum GIS. Similarly, there is a very popular programming tool known as the R. So this r.avaflow is one of the popular open source mass flow simulation model, which not just simulates the avalanche, but it can also simulate the debris and the glacial lake outburst flooding. So if you have some compound disasters, so this is one particular model where the research community or the some agencies, those who are interested in modeling such kind of compound hazards, they can make use of this open source model. And some of the recent publications like the Chamoli disaster of 2021, that was also used, that have also used this particular model for the compound disasters. Then once that snow is there, but we know that there is a reduction in the overall changes in the precipitation and temperature, and temperature change has been mostly in the warming scenario. That means the air temperature has decreased. So that decreased air temperature will lead to formation of such glacier lakes. This particular example is of the Imja Tasho Glacier Lake, because glacier is moving forward this direction also, and the companion glacier also it is moving in the forward direction. But this side it is normally land terminating glacier, but here in 1970s few supraglacial lakes joined together to become a bigger lake. And once the glacier starts draining into a lake, due to the conductivity and the thermal heat capacity of the water, the ice will directly calve into the lake, so it will have more retreat as compared to the land terminating glacier, as has been proved by the various published literature. So this is four cascade of the lakes. This is example of the Bhutan, where in the North Bhutan we have this three glacial lakes, where in 1994 this Rashprang lake actually drained, 50% of the water drained, caused the heavy floods in the downstream. This one example of the Parichu lake in 2000 and 2004, where it is not the glacier but due to a major landslide, where the cause may not be known. So that landslide blocked the path of the lake, and then in the mid of the night this lake drained, and lot of flooding took place in the downstream areas. So this is one example of Dholi Ganga in the Niti Valley. Then this is the Lonak Lake in Sikkim area, and these are the lakes in the Mount Everest complex, including Imja Tasho, and these are the dangerous lakes in the Bhutan area. So these lakes, then in Himachal we have this Gipangat glacier, which is being regularly monitored by low to high resolution satellite data. So you can also see the growth of this particular lake from 1970s to till now. So this particular lake has a natural drainage here, and then from the satellite observation and this one, so the total lake area has increased to 0.93. Now it is almost 1 square kilometer. So the modeling of such lakes is also done to see how much downstream area will get damaged. And recently we have also purchased very high resolution digital globe digital elevation data from lake to the Sisu site. So if you have the better digital elevation model, and also we had planned this bathymetry survey, but due to some logistic reasons we could not complete it. But next year we will also conduct a full bathymetric survey of this lake to get the accurate estimate of the volume, so that our simulations in this particular area, they are more accurate. And then these are the some of the instruments that we make use of, the measuring, for example, the river cross sections, or for measuring the depth in a particular lake using the echo sounder. Then we have this simulations in the Padam Lake in the Jangsar Himalayas, where we assume certain depth of the lake, that let us say there is a mean depth of 10 meters, and then this entire or the 50% of the water will breach in 2 hours. So the peak flow is 21 cumex, and then you can see in the downstream areas what are the villages which are going to be inundated. So you have the base data, which is the latest high resolution remote sensing data, and then you can, in this case we have used the publicly available DEM, but if you have the good quality DEM, you can also generate the exact and more accurate these inundation scenarios. And then these glaciers, because not just the glacier lake outward flood, the avalanche will happen. So some of these glaciers, when they are retreating, these are the portion known as the lateral moraines. So this lateral moraines, this is a Meru glacier contributing to the main Gangotri glacier here. So as you can see, from 2010 to 2016, as the ice has moved, there is a water channel from this Nila Tal which has started developing. So then suddenly in 2017 monsoon, there big debris flow occurred. So that monitoring with the satellite data, and how the river has shifted. And then we have the different date digital elevation model, and also RUMS based debris flow model, which can give us the accurate estimate of the how much volume which is eroded, and how much area of the water this soil is deposited in the downstream area. So this, although we have not used the commercial satellite data here, but you can see in July 2017, few days after this particular event, so you can see water still seeping through here, because in July August temperature will be higher, and a lot of melt water from the Raktavaran glacier, and then there is a small layer of surface water which is seen over this debris. So although event has already occurred, then still this process is continuing, its area is increasing, and the repositioning of the sediment being transported in the downstream of the Gomukh snout. And then one example here, where we have this hydro landslide in the great Namchi Barwa area. So this particular area, this is a glacier, but due to this anthropogenic and other reasons, there was a huge landslide combined with the debris flow, which blocked the path of this Sarlang Zangpo, the name of the Brahmaputra river in Tibet region, Tibet autonomous region. So this is the normal 2017. This is during 2018. So this blocked the water, and after 2 3 days, when there was a breach, so the peak discharge went up to more than 40,000 cubic as after the hydrodynamic simulation, and this is the actual water level which was observed at the tuting by the Central Water Commission. So such kind of hazards also can be monitored in near real time using satellite data. And then this was a very huge disaster which actually nobody had actually thought of, because it occurred in the middle of the winter. So middle of winter, so snow avalanches was known, but such a big rock fall plus the ice plus the snow and this entire debris from the height of this was initiated by this almost 1700-meter vertical ice fall, and then the hydropower was very short distance here, and slope was very high. So entire this water came with the debris, and in the pre-image and the post-image, you can see here more than 100 meter of the water flood water was observed using the satellite data. So such kind of events. And then you can also see a planet image here, which is taken few minutes after the disaster, and it is at the Rani village. It has still not reached the Tapovan site. So if you have the programmed commercial satellite or our own EO data, so then in near real time we can see from where and how this disaster is occurring. And then that is in the head reaches. Once the you have excess water in the head reaches, it will come to the flood plains. So the our northeast India and the monsoon overall India will have the cloud cover. So to monitor this one, we will go for the SAR data. And SAR data, due to the higher wavelength than the hydrometeors in the clouds, it will penetrate the clouds, and then you can see, due to the smooth surface of the water, these microwaves will have the specular reflection from the surface of the water. So this data has been used for monitoring of all the floods. And then for the modelers who are involved in the hydrodynamic modeling, we take this data as a ground truth. So for example, if I am simulating this flood in this particular area, so whatever simulation we do, our maximum flood extent should match what we see in the ground or what we see in the satellite data. So this will help us to plan in the future, and also to make the flood hazard maps. So if you have the 30 years of the satellite data, so you know which pixels or the areas which are flooded each year, which are flooded once in 30 years. So this will also help us to make our flood plain management plans in a better way. Then recently, this lot of heavy rainfall took place in this Indus region. So in 2010 also we had lot of floods, but in 2022 also, if you see the 31st August and 3rd May image of the resource set, so here also you can see this area, lot of area gets flooded in this particular lower Indus basin. So satellite data will be a valuable tool. And if you see for the mountainous region, so if you remember 2013, there was a flood, not in the floodplain, but in the early summer in the entire Uttarakhand. So these are the flash floods, and our satellite data, radar data may not be able to capture such a high slope, high relief area. So what we do to monitor the flood damages, or to see what are the areas which are damaged. So what we do, we take the pre-flood image. This is a pre-flood image of the but in this Hanuman Chatti to Govind Ghat area of the Alaknanda river, and then this is the post flood image of the same area. So you can see here the river, main Alaknanda river, coming from the Badrinath side. The river channel is almost same what was before the floods, but suddenly at the below Hanuman Chatti, this particular branch, you see there is a width will rise from 10 meter to almost more than 60 80 meters or 100 meters some places. So that means this particular valley has received the excess rainfall, or the cloud burst has happened in this particular side. Similarly, the other tributary valleys, we don't see significant increase in the width, but once we go to the this valley of flowers upstream of the Govind Ghat, you suddenly see there is an increase in the width of the channel. So that indicates indirectly that this particular valley has received very high rainfall, and this particular valley has also received high rainfall, and the flood water has gone up to this point, which is actually visible. In actual reality, it may have gone slightly above also. So this is the area where a lot of damages took place, including a big damage to the hydropower project in that particular area. So this is the same area in 2017. So if after next 30 years, if we don't have the flood in this area, so there will be vegetation and other things. So people may get a false sense of security that this area is not getting the flood. So if you have the full time history, at least last 30-year time history and the space history of these areas, we will know how much time this area got flooded, and then we can calibrate and validate our hydrodynamic models, satellite based precipitation products based upon such observations, satellite observations in the mountainous regions. Then sometimes we have to get the first hand information about the inundation. So this is just a example where we use the topography based compatible with GIS. The common tool is hand above nearest drainage. There are other tools also. So if we have the good topography, so I can make the connecting pixels, and then we can say that water will rise by 1 meter, 2 meter, or 20 meters. So immediately along that river system, we will know that which area are prone for the flooding if the water level is rising by a certain meter. So although may not be that much accurate, because it is only connecting the DM pixel, but in absence of any data, this may prove useful for the rapid flood assessment in the mountainous or the high relief regions. Then because these days we have a lot of commercial companies. This one example from the ISI. So this is a new space age company where they have made a small commercial synthetic aperture radar satellites, and they can monitor on daily basis. So although their main customers were in the ocean and the commercial domains, the shipping industry, but now they have also started ventured into the with the collaboration of insurance company, the near real time flood damage assessment, including how much area is damaged, and then they combine this information with the high resolution element at risk. That means how much blocks industry or the human settlements are getting affected, and what is the flood depth. So those location also with the very high spatial resolution, and then they will see this data not just at the when the data is available, but the cover the entire flood peak at the maximum flood water extent and also at the minimum flood water extent, because these satellites that can be programmed, and you can get it this data at every half an hour or sometimes low. So these are some of the companies like Kepler Space, Spire, Planet, and now Indian company Pixel Space. They also aspire to give you the first constellation of the hyperspectral imaging satellites. So although this data is commercial, you have to pay from your pocket to get this kind of very high resolution images. But in case of the disasters, as we know, the cost is human cost and the infrastructure cost is very high. So if you can afford this, you can have this information, which can actually be used in for the insurance purpose as well. Then this is just one example from the altimeters, how we can get the satellite based water level. So this height of the satellite minus the range, the distance of the satellite or the two-way range here, and then we make the correction for the atmosphere, ionosphere and the tidal. So this will have the centimeter level accuracy, and all the major water bodies can be covered. Only limitation is the temporal resolution, which in the future you will have the constellation of the satellites. So one of those constellation is Smash, where you will get almost 10 satellites in orbit in the Ka band, and then you will get the daily coverage of the water level. But in immediate future, you will have I think this December or January, the surface water and ocean topography mission, where you will get for the first time the river height, width, slope and discharge at every 10 kilometers for all the rivers with having widths 100 meters, and 200 meter product for river height and width. And this lake storage changes also for all the water bodies greater than 6 hectares. So it has a this Ka band interferometric SAR, which will give you the swath based water level, and you have also have the traditional altimeters. So all this data we make use in the, because all the time satellite data cannot be there, and some places we have to make sure that our forecasting system is also in place. So for the flood forecasting, this hydrological modeling is the first. The first is the weather forecasting. Hydrological modeling is the second one, where in a GIS environment we will combine our digital elevation model, soil, land use, and this curve number from these two information, and then once we have the input rainfall, we will generate the hydrograph. So these are some of the inputs: topographical, meteorological and land surface, which help us to improve our hydrological modeling. So this is just an example of these models, where we use this model for snow melt runoff, rainfall runoff model to get the water estimate. Plus the once the water comes from the high mountainous region, and using the digital elevation model and hydrodynamic models, we can generate the inundation scenarios. And these are some of the models of hydrological models, and these are some examples of the hydrodynamic models. And this is one example where you have the 3 days weather forecast. This is 2015 flood event in the Beas and Mandi, this Mandi and Kullu districts of Himachal, where this Dharampur region of Mandi got very heavy cloudburst kind of rainfall, and entire area, this entire the bust in, you can see the top of the roof of bust, the water is coming here. So this was simulated with the weather forecast. This data put into hydrology to get you the flood hydrograph, and then these are the inundation scenario. So these are the some of the steps which are used to generate the flood model. For example, the from the precipitation you generate the runoff. That runoff has to be generated. How much in a excess runoff converted into the river system through the unit hydrograph, and then using some stream flow data we measure it, and then we do the routing from point 1 to point 2, how the water will flow. So this combination of meteorology, hydrology and hydrodynamic models give us the integrated scenarios. So this tomorrow also we'll discuss. Just an example I have given, Beas Basin. So if you have the sub-daily rainfall and sub-daily discharge, you can get very high accuracy within the hydrological models. So this is the hydrological model output. This is the hydrodynamic model output for the Beas Basin. And in both the cases, here DM is used to generate the watershed boundaries. Here the DEM is used to get the river topographical data to get the inundation. Then this is one example where we have evaluated various satellite based and the reanalysis data, and this numerical weather prediction models, and the ground observation data, that if we change the meteorology, what will be the impact on the this hydrological model. So you can see here various sources, and this is from the various IMD data sets. And then here you can significantly see Haridwar T, and this without the Tehri Dam. So Tehri Dam has reduced the peak flow which came at Haridwar by almost 7 to 9,000 cubic. So because it happened in early monsoon, so this Tehri Dam was empty. So entire floodway from the Bhagirathi basin was absorbed within the Tehri Dam. But the same may not be true if the thing happened at the end of monsoon. So I'll show one example there also. And then this entire thing is automated now. We are automatically doing this hydrograph generation from the given meteorological input data. And this is the for example of Kerala, where the flood happened in the middle of monsoon and then again at the almost end of July and then middle of August, when the reservoirs were full. So in those cases, when the reservoir is full and the rainfall big storm is still coming, you will have more damages in the downstream, because you have to open all the gates of the reservoirs. This is just example of Iduki here. This when the dam was opened, all the gates were opened for the first time. So you can see in the downstream area, this is the actual photograph from the media, and this is the after the floods, and this is the simulation results for the same area. Then apart from the simulation, this GIS, if you multi GIS layers, if you are able to combine it, you can also generate the flash flood map. This is the example of the Bias River Basin, and the corresponding paper you can see for this particular link. So these are the areas Manali to Bhuntar which are more vulnerable for the flash floods. Then this one example of the urban flooding, because Bangalore, Jaipur, Chennai, Srinagar, Delhi, Gurgaon, many areas, Ahmedabad, so many areas have seen the rapid urban exponential growth. So once you have the more urbanized area, your infiltration will be less, more excess runoff. So although Dehradun is blessed to have the natural slope, but if you have the very heavy rainfall, for example, this is 50 millimeters per hour in 2017. So this is the subdaily hydrograph and then corresponding hydrograph here. So it caused flash floods for 3 hours in the main city, and you can see this Rispana river and Bindal river. Their entire river is constrained due to the human activity, and within that constrained channel, you see lot of solid waste being dumped into the both sides of the river, and then you can see streets and other things which are getting flooded. And in the normal excess rainfall case also, you can see many government and some commercial space activities which are happening, which gets flooded due to the what you can say, the planning was not proper, so that the sufficient space is given to the natural drainage to let the excess water pass through. So the same thing these days, we have the commercial models and the public models like the stormwater management models. So at every hourly basis, I can know which ward will have the high excess water. So this way, this high resolution remote sensing data, DM data, and the MET data will help us to demarcate accurately what are the areas which are going to be flooded. Then this year again we have the cloud burst, almost very heavy rainfall, although not cloud burst because rainfall was not of that category, but still we had the very heavy rainfall events in the day, and then in the night also on 19th, 18th, 19th, 20th August 2022. And in the Maldevta, which is a very popular tourist site somewhere here. So in this particular area, these two catchments, so this one, these two tributaries, and this is Maldevta here. So they have this more than 540 meter cubes of the water coming at the middle of the night. So this is at Maldevta, and this is at the bridge site. So you can see here before this flood, lot of construction activities are going on right in the middle of the river, which is actually the floodplain of the river. This particular house you can see here. So this excess rainfall, although it is not in the cloudburst category, but it may have the recurrent interval of 25 to 30 years. So you can see here the river has reclaimed its path, and then one of the bridges there, which is on the airport road, that also got washed away. So such kind of events, if we make the unplanned human activities in the main course of the river, they are bound to have the repercussions like this what we have seen in the Maldevta side. And these are the some of the future sensors like the NASA ISRO SAR, which will have the very first time you will get the interferometric pairs for the cryosphere, for the biosphere, and for the solid earth. And here you can see the dynamics of the glaciers, the dynamics of the snow, and then you have the dedicated mission for the surface water and ocean topography. Plus there are a lot of observation data which is continuously being generated. So this is from the space agency, but as I told earlier also, there are private space players also. If you have the sufficient funds available with you, you can task them to the near real time monitoring of disasters. And if you have the good quality base data in terms of ortho rectified image, digital elevation model, good verified soil data, and also the near real time weather data from the meteorology, from the weather station, from the satellite based precipitation, you cannot avoid such disasters, but at least you know what are the areas which are going to be affected by such disasters. You can plan them in a better way, and in future we may have full commercial activities like the insurance in this particular sector, which will again need a lot of inputs from the satellites and the geospatial platforms. So thank you all, and in next 4 days, dedicated lectures will cover the topics like drought, snow avalanches, glacial hazards, hydrodynamic modeling, flood mapping, and also hydrological modeling for the flood peak generation. Thank you.